Hello, so in this video we will talk about the so-called inclusion-exclusion principle. So let's start with the definition. So the definition goes like this. If we have A1, A2 up to AN are finite sets, then the cardinality of A1 union A2 up to AN, this is equal to this expression. So this is AI minus AI AJ intersection here. Note this is intersection and this is union. Then plus AI intersection AJ intersection AK. Then we have minus, then we have plus, and the last one is minus 1 to the n plus 1 intersection or a cardinality of the intersection of all of them. Okay, so this is the inclusion exclusion principle, and now let's prove it using mathematical induction. So we'll say base step. So this proof is using mathematical induction. Okay, so this is base step. Now for base step we have n is equal to 2. Then all we have to prove is that A1 union A2, the cardinality, this is equal to A1, the sum of both of them, subtract A1 intersection A2, cardinality of it. Okay, now this can be easily seen using the Venn diagram approach. So then let's say this is my A1 and this is my A2. So A1 here and A2 here. So the cardinality of A1 will be all this area, and the cardinality of A2 will be all this area, and cardinality of A1 union A2 is the total area of them. But note that this intersection is colored twice or shaded twice. Okay, so then that's why we have to take away one of them. So this is my, this shading is my A2, this shading is my A1, and this is my A1 intersection A2. So that's why I have to take away this once, because this is shaded twice. Okay, so then we have proved diagrammatically we have proved that A1 union A2 cardinality is equal to the cardinality of A1 plus cardinality of A2 minus the cardinality of their intersection. Now let's say the inductive step. Let's start inductive step here. Inductive step. So what is our hypothesis? Our hypothesis is that A1 union A2 up to AK union here, this is equal to AI up I is equal to 1 to K minus AI intersection AJ plus minus up to minus 1 to the K plus 1 A1 intersection A2 up to AK. Okay, so this is our hypothesis. So now we have to find an expression for A1 union A2 up to union A K plus 1. So this is what we want to find. Okay, so what I will do is I'll say let B, this is equal to this whole thing. So I'll say let B is equal to A1 union A2 up to union AK. So then what we want to find is B union AK plus 1. Correct? Okay. So then using the base step or using the inductive hypothesis, what is B union AK plus 1? So this is equal to cardinality of B plus the cardinality of AK plus 1 minus the cardinality of B intersection AK plus 1. Okay, this makes sense because this is the same as this guy here. Okay. Okay. Now what we want to do is we want to write B union AK plus 1. Now what we want to write is B intersection AK plus 1. So this is equal to A1 intersection AK plus 1 union A2 intersection AK plus 1 union up to AK intersection AK plus 1. Okay, so this is due to the distributive law. Okay, because if I expand B as A1 union A2 up to AK, then it should be A1 intersection AK plus 1, and all the components of B are intersected with AK plus 1, and the union is taken in the end. But this I can again expand because they are K sets here. 1, 2, up to K sets. Every AK is getting intersected with AK plus 1. So there are K of them. So I can use the inductive hypothesis to expand this guy. Okay. So now let's do it. Okay. So then what we have here? We have first of all, so this is equal to summation of all of them. AI intersection AK plus 1 minus AI intersection AJ intersection AK plus 1 plus and then minus again. The last one will be minus 1 to the power of K plus 1. This should be plus here. A1 intersection A2 intersection up to AK plus 1. Okay. Now let me write it. Let me write this one with the full story here. So what we want to do is we want to say B union AK plus 1. This is equal to B, cardinality of B. B is what? A1 union A2 union up to AK plus cardinality of AK plus 1 minus, so if I call this equation as 1 minus equation 1. Now this, because of the inductive hypothesis, so this is equal to I can say AI minus AI intersection AJ minus plus plus minus 1 to the k plus 1, cardinality of A1 intersection up to AK. Okay, okay, and then I will write AK plus 1, so plus, so this is I is equal to 1 to k here. So this is also I j from 1 to k here. Then I will write AK plus 1 here. Why? Because of this term. And then we have this whole story of 1. So let's expand this. So I can say minus of AI AK plus 1 plus AI AJ and AK plus 1, and then minus plus, and then I will say minus 1 to the k plus 1, this whole story here, A1 intersection A2 up to AK plus 1. Okay, now this is nothing, so if I add this term here, so I will end up as AI and summation I is equal to 1 to k plus 1. If I add this term to this term, this is nothing but I is equal to I and j is equal to 1 to k plus 1 and I less than j. Okay, the same thing, AI intersection AJ, and then you can appreciate that this term is the same as the third term on this summation. So all the terms will add up appropriately. And why is that? Note that this is all the intersection of all the pairs without k plus 1, and this is all the intersections of B or all the a 1 to AK with AK plus 1. So if I try to merge this summation and this summation, the only thing will change is that IJ will go from 1 to K plus 1, and you will appreciate that this is the case with each case, each each term which is a summation for the overall summation here. Okay, so then I will say plus minus 1 to the k plus 2 a1 a k plus 1. Okay, so this is actually, we have proved that this is our inductive step is now proved. Now remember, where did we start from? We started from, so this is equal to a1 union a2 up to union of a k plus 1. So this is where we started from, and then our inductive hypothesis was that this is true for up to ak, and now we have proved it for a k plus 1. Okay, so now this statement is true for any integer k. Okay, so this was the formal proof of the inclusion exclusion principle. And if you see some text, they also talk about some proof in which they assume an element in all of in a specific number of sets, and then they check that okay, this term will make sure that that element is only counted once. So this is another strategy you can employ, and I have no you know uh, no bias for any strategy. I like mathematical induction because it is for integers, it always works. Sometimes it makes our life a little bit harder, and if you can find some cool trick like what I'm trying to tell you right now, using an element and checking whether it is counted only once or not, then it's good. But mathematical induction, you have the safety of saying that it will always work. Okay. Okay, now let's see an example of this inclusion exclusion principle. Now we have 270 college students and 64 like one type of vegetable, 94 type like another type of vegetable, and 58 like another type of vegetable. And there are some other kind of information here as well. So first of all, what we will do, we will say A1 is the set of students liking Brussels sprouts. And similarly, A2 is the set of students liking broccoli, and A3 is for cauliflower. I am in A3 by the way. Okay. Then the information is A1, this is equal to 64, A2, this is equal to 94, and A3, this is equal to 58. There's another information that A1 uh, A1 intersection A2, this is equal to both broccoli and Brussels sprouts, so 26. A1 intersection A3, this is equal to both Brussels sprouts and cauliflower is 28. And A1 intersection A2 intersection A3, this is equal to 22, and 14 like all of them. So and then A1 intersection A2 intersection A3, this is equal to 14. What we want to find, we want to find which do not like any of these. So first of all, what we want to find, we want to find A1 union A2 union A3. Okay, so this is equal to, by inclusion exclusion principle, this is equal to 64 plus 94 plus 58 minus 26 plus 28 plus 22 plus 14. So this is equal to what? So 94 plus 64 is 158, 158 plus 58 is 216, 216 minus 26 is 190, 190 minus 50 is 140, 154. So then not liking any vegetables, this is equal to 270 minus 154, which is equal to 116. And if you know the basic formula for inclusion exclusion principle, there it's just plug and play with numbers and just addition subtraction. So just a recap, if you remember this formula, then you can handle any problem which is of this form. Okay, so this is it for the inclusion exclusion principle, and followed by a simple example how it is used. Thanks for watching the video, hope you like it.